Okay, now, we make a formal definition. D of uv stands for the distance between two vectors. We've already defined that as being the magnitude of the difference of the two vectors. So here's our definition of distance between two vectors. Using this definition and not some vague explanation, which often has a lot of good substance to it, but isn't specific enough to build on, to being sure that you have it right, prove that D of uv equals D of vu. Because does the order here matter? Is this commutative? Okay, is this distance property a commutative, and in this case actually reflexive property? And we don't need to worry about those terms at this point. Okay, so how would you write out a proof of this? Okay, well hopefully you've done it, but here's another hint. I would start out by representing u and v. Okay, how would you write out u and v? Now these are vectors right now in Rn. We can generalize this to other kinds of inner products, just like dot products, but calculated a little differently, but with the same properties as dot products, okay? But right now, we're just in Rn, Euclidean space of whatever dimension, 47 dimensions. How would you write it out for an n-dimensional vector space? How would you represent u? How would you represent v? So what would this equality look like? Well, hopefully you've done that, but it would be now you could choose another notation, but I think this is the most convenient notation. It's the distance between this vector and Vn, and you're trying to prove that that equals the distance between V1, this, and now you're probably saying, well, it's obvious the distance doesn't matter what direction you go. You're right, but I want to see notation that makes this argument airtight so you can really make that statement with confidence and verify it anytime you need to by redoing this proof, at least in your head. Well, that's going to be, by the definition, okay, what's our definition? It's well, this, okay? It's the magnitude of W minus V. So that's going to be magnitude of, in this case it's U and V. The first statement is going to be the magnitude of V minus U. Okay, so that's going to be the magnitude of, now I'm going to way more trouble than we would ordinarily go to once we're used to this, but I'm going to write it out in gory detail and then talk about how it could have been written out a little more efficiently. If I can write U's where I mean U's and V's where I mean V's at the same time as I'm talking, I'll consider it a victory. Okay, this is a U. Okay? And that should equal the magnitude of U1, U2 through UN minus V1, V2 through Vn. That, okay. I don't want an equal sign here, and I do want people to be kind of careful about that. So, this first represents distance of this. Okay, that should be equal to the second, which is this. Okay, so now our next step is, well, okay, it's going to be the magnitude of what? V1 minus U1, V2 minus U2, up through Vn minus Un. Okay, that's this one. What's this one? Write it out. Stay a step ahead of me. Pause until you've got it. Now, the only difference is I've written these down, but with the U component first, because that's the way this one will work, okay? This minus this, according to the definition. So what's this? Well, now I could write out the dot product definition, but let's assume that we are comfortable with that. So maybe I'll put a few dots here to indicate that, yeah, we're kind of skipping a step. But it should be clear then that this magnitude is the square root of the dot product of this vector with itself. Okay? And let's just write that out. Okay? So, just off to the side, and I'm probably going to erase it before I go too much further. And I'm kind of abbreviating it and trying to remember to write U's when I mean U and V when I write V. That's what I mean by the magnitude of this, the dot product of this vector with itself, meaning write it as a row, write it as a column, and then multiply it out. And when we multiply it out, well, we have V1 minus U1 times V1 minus U1. Well, that's V1 minus U1 squared. And up to Vn minus Un squared. And I could have written a couple more, you know, V2 minus U2 squared plus V3 minus U3 squared. Would have gotten monotonous, then we could just skip with dots up to Vn minus Un squared. So, writing it out a little more in detail here, just writing a couple more steps. V1 minus U1 squared plus V2 minus U2 squared plus Vn minus Un squared. And that's this one. Now, if I do the same thing with this side, what do I get? Well, it's U1 minus V1. And if I write it out this way, it should be obvious what we get. It should be this. Now, is this equal to this? Well, I take a second to erase this because it's not going to take much room to establish the result. And hopefully we can do that without too badly chalking up the board. Why should this be equal to this? Well, yeah, this is something that people weren't real clear about. Let's consider this. How is 5 minus 3 squared compared to 3 minus 5 squared? What is the difference? Well, 5 minus 3 squared is 2 squared. 3 minus 5 squared is negative 2 squared. Either way, you get 4. So this equals this, therefore this equals this, and this equals this, right? And generally, A minus B squared is equal to B minus A squared. Can you prove that? Stop and see if you can prove it. And you can't prove it just by saying, well, it worked for 5 and 3 and it works for every other pair of numbers I can think of. It works for reasons that are based on the foundations of algebra, just plain old algebra 1 algebra. So prove that this equals this. Well, hopefully you've done that. I'm going to go ahead and do it. Well, a minus b quantity squared is a squared minus 2ab plus b squared. B minus a squared is, well, let's see, it's b squared minus 2ba plus a squared. And now if we simply change our order, we see that they're identical. And if you don't see that they're identical, well, go out and get a little counseling. It's not, seriously, it's not a mental illness. Email me and I'll be glad to explain it to you. That just goes back to properties of commutativity and associativity. And you really should be able to work that through in some detail using commutativity and associativity. How does that help with this proof? Well, A and B could be anything. So if A and B are B1 and U1, then this has to equal this, right? And this has to equal this. And every one has to equal the one you have here, because it doesn't matter in which direction you subtract two numbers. When you square them, you're going to get the same thing. So that kind of completes the proof. Now, I haven't written out the details. You should address every detail, including understanding that you have to address this detail, and understanding that maybe you got to play with a few numbers before you believe it, and then work out how you write it out algebraically in symbols.